Right. So yeah, we're excited to begin the last block of speakers for our conference. And we'll begin with Joel Kamnitzer, who's going to tell us about BFN Springer theory and the Hikita conjecture.
Okay, thanks very much to the organizers for organizing this very nice conference. I don't even know if this was originally going to be a regular conference and then you guys turned it online, or if it was a purely online effort, but either way, thanks very much. It's nice to sort of see lots of familiar faces and hear them too. Okay, so this is joint work with Justin Hilbrun and Alex Weeks. It just went on the archive about a month ago during the lockdown period. So, so what I'm going to talk about is related to this theory of Coulomb branches. So there was already, I guess, one talk, Alex talked about it a bit before, but I'll tell you much more, I guess, or a different take. Okay, so let's begin. So suppose I have a reductive group, G, and G will almost always, for me, just be a product of general linear groups. So maybe associated, most likely associated to a quiver theory. So you may have some quiver, and then associated to the nodes of the quiver, you have general linear groups, and this G will be the product of those general linear groups. So that's the kind of G you should think of, but it could be any reductive group, and V any representation of G. And again, the typical example for me would be when V comes from such a quiver theory, so it's associated to the arrows in the quiver. And from this reductive group and the representation, physicists study a gauge theory, specifically three-dimensional n=4 supersymmetric gauge theory, and they are interested in two spaces that are defined, two hyperkähler varieties, hyperkähler manifolds. And one is called the Higgs branch. So the Higgs branch has a relatively simple definition from mathematicians, even for physicists. So we take V, we take its cotangent bundle. Since V is just a vector space, that just means we take its direct sum with a dual space. And then we take the hyperkähler reduction of this cotangent bundle by G, or I guess by the compact form of G, which is the same as the complex symplectic reduction of this cotangent bundle by just G. So in other words, in the complex symplectic world, I take the zero level of the mode map, and I take the projective GIT quotient with respect to some character chi. So here chi is some character of G. So this construction, I think, is familiar to many people. For example, produces Nakajima quiver varieties, hypertoric varieties, hyperpolygon spaces, which appeared earlier in the talk, and many other familiar examples. Cotangent bundles of flag varieties, full and partial flag varieties in type A. So many natural spaces come in this Higgs branch construction. And then physicists have a second, more mysterious construction called Coulomb branch, which has also recently been given a precise mathematical definition in the work of Braverman Finkelberg and Nakajima. So I will explain more about that soon. But let me give you a rough definition. So roughly, we start by producing a certain algebra and then take spec of the algebra. So if we have an algebra, we take spec that produces us an affine variety. Now, what algebra do we take? Well, it's a bit of a funny algebra. It's defined as a convolution algebra. So it's defined in homology convolution algebra. So it's the homology, we construct a certain space, and then we take its homology, and that has a algebra structure by the virtue of the geometry of this space. And what's the space? Well, again, this is roughly. It's going to get more precise in a minute. Roughly, it's a space of maps from P1 into the quotient V by G. Okay, so soon I'll give a more precise definition of this Coulomb branch construction, but before that, let me give an example. So, very simple example, I'll just take G to be C star, V to be Cn. In this case, this Higgs branch, oh, sorry, I guess my slide is slightly inconsistent. This Higgs branch kind of comes in two flavors, depending on if you take a projective GIT quotient here or an affine GIT quotient. And I guess above I wrote the projective GIT quotient, and in the example I wrote the affine GIT quotient. So if I'd been writing the projective GIT quotient here, the Higgs branch would just be the cotangent bundle of projective space. corresponding affine GIT quotient is square 0 matrices of rank less than or equal to 1. But it's the same, the projected GIT quotient would be the cotangent bundle of En minus 1. On the other hand, turns out in this case, the Coulomb branch is also a very simple variety. It's just C2 mod the action of the group Z mod N, acting on each factor in the opposite way. Okay, so let me explain the definition of the Coulomb branch. And again, this was due to Braverman Finkelberg and Nakajima. So definition is a little bit involved, and it uses the affine Grassmannian of the group G. So first of all, let me define this affine Grassmannian. So I take the field of Laurent series. Inside of it, I have the ring of power series. And the affine Grassmannian is the quotient of the group points over Laurent series divided by the group points over power series. So for example, when G is GLN, as I mentioned, that's kind of my main example, this affine Grassmannian can be identified with the space of O lattices in K to the N. That's maybe potentially a more familiar description of it. Another equivalent description for those who are like compact groups, this affine Grassmannian is the same as the base loops into the compact form of G. So sometimes called base loop group. And it's a kind of infinite dimensional analog of a flag variety. So yet another way of thinking about it. Okay, so over this affine Grassmannian, I'm going to introduce a vector bundle. The vector bundle, the fibers will be infinite dimensional. They'll look like V tensor O. And how is it defined exactly? So it's pairs of a point in the affine Grassmannian and a vector. The vector lives in V tensor K, but also the vector should be contained inside the translate of V tensor O by this element G. So I mentioned before that when G is GLN, the affine Grassmannian can be thought of as a space of O lattices in Kn, and this is simply the vector bundle where over each O lattice, you put that O lattice. So it's a kind of tautological vector bundle. Then we do a construction which is familiar from the analog with the flag variety setting. So I want to think of this vector bundle as being kind of analogous to the cotangent bundle of the flag variety. And for the cotangent bundle of the flag variety, there's a familiar construction for forming a Steinberg variety. So, which is that you take two copies of this guy and take its fiber product over the nilpotent cone. So in this case, we take two copies of this vector bundle and take their fiber product over V of V tensor K. So a point in this Steinberg-like variety would consist of 2 points in the affine Grassmannian and one vector which lies in the lattice associated to both of those affine Grassmannian elements. And by the virtue of the fact that it was constructed in this Steinberg-like way, its homology will inherit the structure of a convolution algebra. What's something special in this situation is that it's actually a commutative algebra. Not obvious, but it is a commutative algebra. Oh, and it's not just homology, but G of K equivariant homology. And moreover, this commutative algebra comes with a canonical non-commutative deformation. We have an action of G of K, of course, like just acting on everything, but there's another group acting, which is this group C star called the loop rotation action, and it's acting on the variable T. So you can scale the variable T, and that gives an action of C star. Equivalently, there's a kind of more geometric description of all this, which involves thinking about the formal disk, and then this C star is acting on this formal disk. Okay, so now we have a commutative algebra and we have a non-commutative deformation. So what it gives us when we take spec of it, we get an affine variety, which is the Coulomb branch, and it comes with a deformation quantization, which is this Coulomb branch algebra, AHGB. So that's the definition of the Coulomb branch. So as I say, it's like a totally complicated, weird definition. Probably no one would have ever thought to introduce this, except that it was motivated, this construction is motivated from the physics point of view. Okay, what do we do with this Coulomb branch? Okay, so one thing that's of great interest is to examine the relations between this Higgs branch and the Coulomb branch. So Higgs branch, again, is just this very simple guy defined as this hyperkähler quotient, and now this Coulomb branch defined in a more complicated way. And these two spaces, the Higgs branch and the Coulomb branch, are known to have many relations, some of them many conjectured relations anyway. They're what's called symplectic dual, so a pair of Poisson varieties. I should say that this Coulomb branch carries a Poisson structure because we've endowed it with its coordinate ring with a non-commutative deformation. So the first order non-commutativity endows this algebra A with a Poisson structure. So this guy is actually a Poisson variety, the Coulomb branch. So anyway, a pair of Poisson varieties that have this relation are called symplectic dual. And it's been of great interest in the past, say, 5 years to try to understand this symplectic duality and all these conjectured relations. So I'm going to discuss one such conjectural relationship called Hikita conjecture. Okay, so now I'd like to formulate this Hikita conjecture. But in doing so, I'll tell you a little bit more about this algebra to begin with. So I mentioned that we have an algebra now, this Coulomb branch algebra. It's the non-commutative algebra, the deformation quantization of the Coulomb branch. And it was defined as the homology of some space built out of the affine Grassmannian. Now the affine Grassmannian, because it's this base loop space, it has connected components labeled by the fundamental group of G. So in that way, it's because of these connected components, also that space Z I mentioned has such connected components, and therefore this algebra carries a direct sum decomposition labeled by the fundamental group of G. And at the beginning of the talk, I fixed this character chi of G, which on the Higgs branch side was used to construct the projective GIG quotient. And I can use it here to collapse, to turn this, well, to construct a map from pi1 of G to Z. So I have this big grading by pi1 of G, like G is some kind of product of GL, so pi1 of G is pretty big. And then I collapse that grading to an integer grading, so I get an integer grading on my algebra. Okay, so algebras with a kind of integer grading are nice because we can study what's called highest weight modules for these algebras. So, sorry, well, okay, that's coming next. Okay, sorry. So first, what do I do with this integer grading? Well, I define a certain funny quotient of the 0th graded part. So I take the 0th graded part and I mod out by all products of a something in negative degree times something in positive degree. So remember, this is a non-commutative algebra, so this order A, B matters. So I take the 0th graded part and mod out by such products, negative times a positive, opposite degrees. So why is that algebra interesting? Here's the reason. So if I have a module for my algebra, I would like to consider modules which have an integer grading compatible with this integer grading of the algebra. And I also want to consider modules which are highest weight. So what that means is that eventually this integer grading is 0. So I'm thinking as analogy with the case when this AH is, say, the universal enveloping algebra of a semi-simple Lie algebra. In fact, the universal enveloping algebra of SLN is an example of this Coulomb branch algebra. So in that example, this integer grading would, or this pi1 of G grading would correspond to the usual grading of my algebra by the root lattice. And here I would have, collapsed that root lattice grading to an integer. And then these modules would be of highest weight. So this would be a grading by kind of weight spaces or collapsed version of the grading by weight spaces. And I would be saying that the weight space there is 0 for large enough weights. So here I'm looking for modules which for large K, their weight spaces are 0. And then this algebra B will act on this highest weight space. Because, of course, the 0th graded part will preserve the highest weight space, because 0 plus anything is that thing. But then these things that I'm quotienting by these products A, B, this B would want to push you into even higher weight spaces, and then A would bring you back. But when B pushes you into a higher weight space, you get 0. So this algebra B would act on M and 0. In particular, a kind of natural situation is when this highest weight space is kind of one-dimensional. Everything here is over some formal variable h bar. So you could imagine this h bar as a number, in which case it really is one-dimensional, or it's a variable. It doesn't really matter. So if this highest weight space is one-dimensional, then this will actually give you an algebra map from this B algebra, this funny algebra I built this way, to CH bar. And I'll think of this algebra map as being the highest weight of my module M. So in the case when, as I mentioned, when AH is some like universal developing algebra of SLN, then this map really will be telling me the highest weight of my module. Okay, so all this was an attempt to build towards the statement of the Hikita conjecture. So, okay, so let me just, before I get there, I'll have to do a little bit more preliminary. So this Higgs branch, so here's my Higgs branch, MH. Remember, that was just defined as the Hamiltonian reduction of the cotangent bundle by the action of G, cotangent bundle of V by the action of G, and therefore we have a Curwan map, or sometimes called hyperkähler Curwan map. This Curwan map. And on the other hand, there's a similar sort of structure, which is called on the Coulomb branch side. So here's my Coulomb branch algebra, and it comes with what's called the Gelfand-Zetlin subalgebra. So it contains a copy of also of this equivariant cohomology of a point in a very natural way, just because this algebra was defined as the equivariant homology of some space, and we just include this in acting on some point in there. And then this is always a complete integrable system. So this is related to what, well, Alex mentioned it, and also Steve mentioned it as well. Okay, so now this is the statement of this Hikita conjecture. So it says that this equivariant cohomology of MAH is isomorphic to this B algebra of this AH. So this is a funny algebra which controls the highest weights of modules for the Coulomb branch algebra. And this is, well, just the equivariant cohomology. And the conjecture is that these two guys are supposed to be isomorphic, not kind of just abstractly. First of all, they should be as algebras. And secondly, compatible with these Curwan maps. Well, the Curwan map and this Gelfand-Zetlin map. So this turns out to be a surprisingly, I don't know, rich statement. It seems a little bizarre, but let's just unpack it a little bit. So to begin with, let me assume that both these Curwan type maps are actually surjective. So I have the usual Curwan surjectivity, and then also a statement that this Gelfand-Zetlin algebra surjects onto this B algebra. So if I assume both things are surjective, or I guess even if I assume one of them is surjective, if I have the statement of the conjecture, then the other one has also got to be surjective. Then I'm just saying that two quotients of some algebra are isomorphic. So two quotients being, there's no sort of data of the isomorphism because they're quotients. And so I can think of each of these quotients define some scheme, some sub-scheme of the spec of the algebra. And I'm just saying that these two sub-schemes are the same. In fact, both these algebras are finite dimensional. I mean, once you set h bar to some number, say h bar equals 1, then both these guys become finite dimensional. And so I'm basically just asserting this, that two finite subsets of this thing are equal. So in particular, this Hikita conjecture predicts a bijection. And the bijection would go between this spec of this guy and spec of the B algebra. Now, spec of the B algebra, on the previous slide, I tried to explain how that spec of that B algebra is related to highest weights or modules for my Coulomb branch algebra. Now, what's spec of the cohomology? Well, if I have here's one way to get a point in spec of this cohomology. Suppose I have a point in a fixed point for my C star action. Then if I have a fixed point for the C star action, I can consider the sequence where I first do the Curwan map, and then I use the map coming from the equivariant cohomology of a point. And that will give me a map from the equivariant cohomology of a point, so an element in this guy, to this C adjoint h bar. And then if I set h bar equals 1, I'll just get to the complex numbers. So that would give me a point in spec of this equivariant cohomology. So in that way, the spec of the equivariant cohomology is identified with the connected components, in fact, of the C star fixed points in the Higgs branch. So in this way, the Hikita conjecture predicts a bijection between maybe a bijection is not even quite the right, an equality between this connected components of the fixed point locus and the highest weights. Okay, so again, this is still a conjecture. I mean, the statement is still conjectural in general. Some special cases of this conjecture are known, but in general, the statement is still conjectural. And I'm going to explain one geometric way that we have of attacking this conjecture, or more precisely, a geometric way of constructing this bijection here. Okay, so in particular, to sort of attack this, I want to produce to every fixed point in the Higgs branch, I want to produce a module for the Coulomb branch algebra. So that's what I'm going to explain now. So more generally, here's a method for producing modules for Coulomb branch algebras. So suppose I take a point V in my space V tensor K. Then I can study what we call the BFN Springer fiber. So I consider all those points in the affine Grassmannian such that V lies in this lattice defined by the affine Grassmannian point. And it's an analog of a ordinary Springer fiber in the fine dimensional case. And if the representation of G is the adjoint representation, then it agrees with what's called the affine Springer fiber. Yeah, but in general, it's its own beast. And so this is this BFN Springer fiber. And then it carries an action of the stabilizer of V. So V has maybe some stabilizer in G of K semi-direct C star. And that group would acts on this Springer fiber, and then we can consider equivariant homology. And the theorem we proved with Justin and Alex is that there's an action of this Coulomb branch algebra on the equivariant homology of this Springer fiber. So here's just a very quick example. So suppose I take G to be GLN and V to be Hom from Cn to Cm. So this is a very simple quiver situation, where I only have like one node and a framing. And V to be some injective map. Then it turns out this FV is what's called the positive part of the affine Grassmannian. It's a disjoint union of these closed subvarieties in the affine Grassmannian consisting of lattices contained in the standard lattice. Okay, so now let me explain how we can use this BFN Springer theory to attack this part of this Hikita conjecture. So suppose I take a point in V which is chi stable. So again, with respect to this fixed character chi, and such that the corresponding point in the scalar quotient V mod chi G is fixed under C star. Then we can prove that the Springer fiber has a very nice behavior in that it's connected. So I didn't maybe say this, but just like the affine Grassmannian and just like that algebra has this decomposition, also the Springer fiber has this decomposition. And in positive parts, it's just empty. There's nothing in the Springer fiber there. The zeroth part of the Springer fiber is simply a point, and the negative parts of the Springer fiber are finite dimensional projective varieties. So it's very nicely behaved. And therefore, its homology, as I said, will define a module for my Coulomb branch algebra. And the theorem is that that's actually a highest weight module. Well, it's easy that kind of follows from what I said here, because it's zero, because it's the homology of the empty set. And then it's the homology of a point, so it's one dimensional. It's a highest weight module, and moreover, the highest weight is given by this same sequence where I use the Coulomb map and then the restriction to the point given by the inclusion of V. So in this way, we've established this part of this Hikita bijection, but not, there's a small problem, which is that I only use those fixed points. My method only uses those fixed points which actually live in the Kähler quotient, V mod mod G, rather than T star V, rather than the full zero level of the moment map, right? This V lives inside the zero level of the moment. We can do slightly better, which is that we can consider different possible G invariant Lagrangians, and it's fact that obviously the Higgs branch doesn't depend on the choice of this G invariant Lagrangian, and actually neither does the Coulomb branch. So in this way, we can establish this kind of Hikita bijection, but only for all those fixed points. For all those fixed points should live in some Kähler quotient inside our hyperkähler quotient. And so it doesn't completely establish this Hikita bijection. Okay, I stop there.
So we can...